Hello friends, let's have a look at an exciting video on the trigonometry and its various proof with using the unit circle. Okay, what I want you to remember is that whenever you want to memorize the identity, you can do that, but also try to understand the proof, because many times, most often time, the advanced questions, the hard problem, would rely on the techniques you applied in the proof. Okay, and of course there are many different proofs in many theorems, like the Pythagorean theorem. I'm sure there are at least 100 different proofs on proving the Pythagorean theorem. But what I want to remind you here is whenever you want to prove the trigonometric identity, it's most often to associate with a unit circle. Okay, so without further ado, let's get started. So yes, I want to remind you that any proof in trigonometry is provable using the unit. So let's take a look at some taste of those theorems using the unit circle. So yeah, and the very first thing that I want to talk about is the Pythagorean identity. You know, the sine squared plus cosine squared is equal to 1. And understanding this really enables you to associate the trig with the Cartesian, with the circle, with the x and y coordinate, which later on will be associated with the complex number as well. So here is the semicircle on the circle, the Cartesian form of the circle is x squared plus y squared is equal to 1. I got that the radius is 1. And on this, let me try to create a right angle triangle like this. Let me try to create a right angle triangle like this. And as you know, I got the hypotenuse here. This is your adjacent. If I have a theta here, right? If I got the theta, then if I have a hypotenuse, adjacent is the 1 times cosine theta. And then the opposite is, if it's a right angle triangle, 1 times sine theta. Okay, that is brilliant. So here, the x and y coordinate on the circle will be cosine theta and sine theta. Very good. So that's what we have. That's great. And then on this, now we had a Cartesian equation of a circle. Then you can plug the x and y coordinate described by the parameters of the radius and theta from the circle into the equation to derive the, Pythagorean identity. So this is the first proof that I wanted to show you, right? Yes, you can memorize this, and then also learn those relevant questions to associate, but the most essential part here when you learn math is how to prove it. And because often those approaches will be critical to derive a clue for solving a hard problem. Now we derive the Pythagorean identity. Let's try to derive another famous one, which is called the double angle formula, just using the unit circle again. Okay, let me try to generate similar shape. I generate this semicircle again, and this time I'm going to alleviate from the horizontal axis to the 2 theta. Okay, so now my x and y coordinate on the circle is derived by the cosine and sine 2 theta using the right angle triangle, right? The adjacent and the opposite, no problem. And then one more thing is that if you remember from your MIP with the deductive geometry, the circle theorem suggests that if I have a point in here, if I have a diameter as a one side, and another side made by the point on the arc, the circumference, it must be perpendicular, right? Because we can use, it's easily provable if we use the isosceles triangle property here. If I call this as phi, this must be phi because it's a radius, and radius is an isosceles triangle. If you add all this, 2 theta plus 2 phi is equal to pi. So if you divide by 2, then you realize the sum must be always pi over 2. It's always perpendicular. The reason I derive this perpendicular triangle is that I can associate now with actually a similar triangle if I make a perpendicular foot here. Okay, so let me try to make a perpendicular foot like that, right? So if you look at the angle ACD of this right angle triangle, and then the right angle triangle that we talked about from the circle theorem must be similar, because why? They have one right angle triangle, and then they have a shared angle theta, so they are similar. That means their ratio is going to be the same. Okay, so the first ratio I'm going to do is a sine theta. So as you can see from the blue small triangle, CD over AC is a sine theta, right? So for that, if I try to find the opposite here from the angle 2 theta, that's going to be sine 2 theta, isn't it? That's going to be sine 2 theta. Yeah. And then hypotenuse is given by 2 cosine theta because of this diameter is 2 because it's a unit circle, the radius is 1. Okay. And then the adjacent from the theta is going to be 2 cosine theta, no problem. Okay. So that is the ratio, must be preserved as the sine, the sine theta in this case. So if I have a sine theta on the large triangle, my friend, the opposite here was a 2 sine theta, and then the hypotenuse in this case is a 2, so 2 sine theta over 2 is what I've got, where you can cancel this out. And then 2 cosine theta, if you rearrange to the other side, then boom, I have the double angle of a sine like that. Okay, so we derive the doubling of sine just using the unit circle as well as a right angle triangle. You can do the same thing for the cosine. If I apply the cosine theta on a small blue triangle and a large red triangle, you realize that the cosine theta here is going to be, what is it? From the blue, hypotenuse and then the adjacent, right? So it's going to be 2 over 2 cosine theta. It's going to be the same as the cosine theta derived from the red triangle. In this case, it's going to be 2 cosine theta over 2, just like that, okay? So then, yeah, easy peasy lemon squeezy. If you rearrange, then you realize the cosine double angle formula can be derived just like that, right? So it is inseparable to associate the proof of the trigonometry using the unit circle. I'll give you one better. Let's try to go with the proof with the compound angle using the, the circle. In this time, I wouldn't call it unit circle because I'm going to use a radius to be half. Okay, so let's just create a circle like that and an inscribed triangle like this, okay, with the length ABC, and then let me call the angle X, Y, Z there, okay, let me label them. So that's great, okay, and then what I'm going to do is, again, if you're trying to derive something off a formula of a trigonometry in a circle, most often what is very helpful, the right angle triangle is very, very helpful. It's very utilizing. And then what I'm going to do here, my friend, is let's try to get the length of a C. Okay? If you ask me to get the length of a C, I'm going to get 2 lengths and then add them together. Well, from the one large right angle triangle there, I got the angle Y, I got the hypotenuse A, and I want to find the adjacent, So for the adjacent, would you use a sine or cosine? You said it correct. I will use a cosine there. So that leg here, I would like to use A times cosine, Y, which we get it from the right angle triangle right away. And then the remaining parts to complete the C, I will get it from the hypotenuse of the B and then the angle X. Okay, let's do that. So if I get the B times cosine X, that's going to be the remaining parts of the leg to complete the C from this yellow highlighted right angle triangle. So let me try to get the B cosine X for the remaining parts of the leg. Adding up together will give you C. No problem. Easy peasy, lemon squeezy. Okay. Now, as I mentioned before, this is not going to be quite the unit circle. This is the unit diameter. Okay. The radius now become a half. Okay. And then let me quickly show you why this angle has to be Z. Well, because of another theorem in the circle theorem of using the deductive geometry, this subtended angle from the same foot will be half of the central angle. Right, so this must be double. So this angle here is going to be 2Z. And then remember, this is an isosceles triangle, isn't it? Because it's an isosceles triangle, if you make a perpendicular foot by the bisector theorem, the angle must bisect. So the angle here is actually Z. You can prove it using the circle theorem like that. No problem. So now I got the hypotenuse being 1 over 2, and then let me apply the sine Z. But because of the bisector theorem, it does not only bisect the angle, it bisects the angle as well, the length as well. So it's going to be C over 2. You know what I'm saying? So now, this opposite from Z, which will be associated with the sine, can be computed as the following. So C over 2, the opposite, all right, it's going to be product of the hypotenuse, in this case half, times the sine ratio. So you can cancel out the 2, then C becomes a sine Z, no problem. Okay? So C is a sine Z, and you can do the same thing on the other. Let's say, okay, I want to associate with something X, okay, if you want, my friend, this X is a subtended angle from this side A, then let me make an isosceles triangle like that, and let me make a perpendicular foot with the similar reason of a central angle being half, but a central angle being twice. But by the bisector theorem, this will be exactly the same as the X. No problem. And then, because of the bisector theorem again, this is going to be A over 2. Right? This is the radius, which in this case half. So as you can see, I can do the same thing. 1 over 2 times the sine X will be A over 2. Therefore, the A has to be sine X, vice versa. I can get those things easily without sweat, all right? And now what I'm going to do is, we said that we want to get the sine compound. Let's try to associate with the sine X plus Y, but sine X plus Y using the reference angle is the same as sine pi minus X plus Y. Again, by the reference angle, remember, if I have a sine pi minus theta, I go pi much and then I subtract by theta, I landed on the second quadrant. Sine is a positive in the second quadrant because it's associated with the y coordinate. So in fact, it will be the same as a sine theta. In fact, this theta is regardless of acute or obtuse. This result always holds. It's quite fascinating, if you ask me. So now, because of the reference angle, I can associate with this. But if you ask me, okay, why did you bother changing it? Well, because I want to associate with Z. Because the sum of internal angles of the triangle has to be pi. And then the angles were x, y, z. But the remaining 2 angles, if you subtract by pi, you get that z. You see, so this is actually same as a sine z. And we just proved the sine z is equal to c, for c, which then we had a cosine y plus b cosine x. However, we just proved using the right angle triangle and a bunch of the circle theorem and bisector theorem that the a is a sine x and b is a sine y. So I'm going to plug it in the a and b like that, which proves the famous compound angle of a sine, sakukosa. Marvelous, easy peasy, lemon squeezy. So I know that you know or you memorize the compound angle of a sine to be sakukosa, cosine compound, kokosasa, but that does not mean that you fully understood, okay? In order to fully understand, you have to know the proof of it, how you derived it, because it justifies all the skills you have learned from the scratch of the trigonometry and often going back to the deductive geometry such as a circle theorem, okay? So it's very important for you to please understand the proof, because often the technique that we just use here, such as reference angle, can be seen in a hard problem, an advanced problem, either paper 1 or paper 3 or paper 2. Doesn't matter, okay? So those deductive skill in the proof is often, again, seen on hard problem, okay? And, you know, I like to go over some hard problem associating those rules, especially with the unit circle, and hence extend it to it. But now I like to derive another result, okay? Going back from May 2011. And here, this is a very famous problem to be able to derive this famous inequality, which you often see in the calculus. So I like to prove up to that part, and then let's carry on solving some hard problems, okay? And especially ones from the exam question. So let me quickly draw the diagram that we saw in the exam, right? It was a unit circle and one large right angle triangle because it was a point of a tangency, and then we draw a chord like that, right? So that what you had to do is that you had to come up with a smaller triangle like that, which I can get it with 1/2, you know, A, B sine C formula, right? For the area of the triangle, isn't it? So that's gonna be just 1/2 r squared sine theta, because it's an isosceles triangle. It's going to be just a product of the length itself. It's going to be perfect square, no problem. And for the, and for the middle part, because that was a small area. For the middle part, that's a sector, isn't it? So for the sector, with the radian measure of the angle theta, it's going to be given as a 1/2 r squared theta. That's the formula that we know, right? That's the sector formula. And then the another formula that I wanna use for the finding out the right angle triangle here. You know, think about it. Right? I got the adjacent, right? And I have to know the opposite to find the, the height of the right angle triangle. I have to use it for the area. What would you do? What is the trig ratio to associate with the adjacent and opposite? Very good. It is to often associate with the tangent. So here, what I want you to do is to use a tangent theta, okay? Then I got the opposite over r. So the opposite must be described by the, r times tangent theta. That is great. So now the large area is going to be half times r squared tangent theta is what we have. Okay? So then we can create the inequality. Who was the least? The triangle was the least, and then we have one in the sector in the middle, and then we have a large area by the right angle triangle. So those are my inequality. Okay? But who is the common factor? I got the r squared over 2 being common factor. I can cancel them out. So if you do, it's going to be sine theta, theta, and tangent theta. Very good. So that's the inequality that was asked in the exam. But you see, often the hard problem is asked because this is a very critical, very essential for many property of the calculus used for trigonometry. Right? For example, the derivative of sine, we use this inequality, etc., etc. So let's get into the rabbit hole of the calculus using everything we have learned so far. Okay? The very first thing that I'm going to do is to manipulate a bit more with the inequality. First of all, the angle that we were doing was coming from the acute angle triangle, the right angle triangle. So we are very certain that theta is in the first quadrant. So sine theta is going to be positive. There's no harm to divide the inequality by the sine theta. It's not going to change the direction of inequality. And all the numbers are bigger than 1. Think about it. If 2 is obviously less than 3, right? If you reciprocate, what happens? Very good. The direction of inequality changes because the smaller the denominator, the bigger the fraction is. So if you actually reciprocate all this, the direction changes. Therefore, 1 becomes the upper bound. That is amazing, right? So that's the inequality that we can extend from the given question in the exam. And from here, what you are going to be learning is something called the squeeze theorem. What we are interested in is this ratio when we send theta to 0. Okay, if you send theta to 0, in this case, I got the 0/0. Okay, which we call indeterminate form. I don't know if it's determined yet, right? So if you look at the ratio, okay, and I don't know what it means, but if you look at the upper bound and lower bound, especially the upper bound is independent of theta, it's just going to converge to 1. The lower bound is also going to converge to 1 because the cosine 0 is simply just a 1. It's 1/1, no problem. So the one in the middle happens to squeeze to the same limit, okay? Let me quickly show you that as an animation. So I create 3 different functions here, okay? Let me show that the lower bound converts to a limit as x goes to 0 in this case. In this case, it converts to 0. And then let me show the upper bound converts to also 1 as theta goes to 0. Just like that, okay? And then the one in the middle therefore must converge to the same limit if it's bounded by the lower bound, upper bound, and they converge to the same limit. It's squeezed to the same limit. Hence the name called the squeeze or Sandwich theorem, depending on whether you're from the UK or US. So that's great. So with this inequality, we can prove that this limit goes to 1, so this limit will also converge to 1. It's called the fundamental limit of trigonometry, which is often used for many parts of calculus in trigonometry. So let's have a look at a very nice, I believe it was a May 2026, or, so my bad, 3, or November. Either way, it was from 2023. So in this limit problem, we can actually use the limit that we just learned, right? So here, I'm given the limit here is a 16. If you're trying to send the limit x to 0, in this case, I got 0 over 0, which we call the indeterminate form. So I need some algebra. You can do the L'Hopital. I don't want to do the L'Hopital because for me, it's God-given, a very simple identity because I can use the fundamental limit of trigonometry right away. I got the sine perfect square, so I just distinguish by the product of itself, and make sure if you want to use a squeeze the fundamental limit of trigonometry, the input and the denominator must be the same. So if I got the kx, the denominator also must be the kx, like that. You gotta match the rate, okay? But I didn't have it before, so I gotta multiply by that reciprocate, so it's gonna be k perfect square. Now you see each term will converge to 1. This will converge to 1, that one is gonna converge to 1. Thanks to the fundamental limit of trigonometry. Please make sure you match the input and then the denominator, right? So then, therefore, I can justify these two limits being converging to 1 because of the fundamental limit of trigonometry. So it's left over with just k squared, okay? And that was given to be 16, so k is plus minus 4. But here the limit was given to be positive real, so I gotta choose k being simply just 4 is what we, okay? So that's great. So that's just one use of the fundamental limit of trigonometry in the exam. And from 2021 to 2024, those limit problem with the association with the fundamental limit of trigonometry has been very popular. So I strongly encourage you to memorize, okay? And now let's have a look at another paper 3 sort of a problem. If I ask you, if you know the derivative of sine, you might say, yes, I do know, it's a cosine, okay? But that does not mean you fully know. You did not justify that you know it fully, because in order to know it, you must understand why. Why is the derivative of sine is cosine? That's a very important question in math. And for that, you have to be able to prove. And in order to prove the derivative, what you got to do is to use something called the first principle. So let me try to use the first principle definition on the sine. So I got the sine x plus h minus sine x over h. That's the first principle. And I can simply put the h to 0. So if I do, I get 0 over 0. Once again, that's indeterminate form. I don't like it, okay? And you might say, okay, then you should do the L'Hopital, but I cannot assume that I know the derivative of a sine unless you prove it. So I don't want to do that. I actually want to use another another technique of trigonometry and association with the fundamental limit of trigonometry to prove it. Let's take a look what I mean by it. So, what we just did on the third theorem with the compound angle, we proved with the half unicircle and then the right angle triangle to derive this cosine. Right now we can use it because we not only memorized it, but also we proved it. So then the difference of angle is going to give it like that because the sine is odd function. You can easily prove it by using a plus negative b. So if you put the negative b, for example, in the cosine, that's going to remain as a positive because cosine is an even function. And because sine is odd function, it's going to come out as negative, no problem. So between these two, let me try to add them together. So those alternating terms will cancel out, you see? And then the same sign, we actually get double, no problem. So let's do that. So I get the twice over sine A and sine B. It's known as the, what is it? It's known as the product to sum formula. This is a product to sum formula, no problem. Okay. And why have I done that? Well, because I want to go reversely. So if you now make a substitution of a plus b is equal to s and a minus b equal to d as a single variable and try to solve it simultaneously to find the solution a and b in terms of s and d, so just simultaneous problem, piece of cake. If you do that, I found the solution of a and b in terms of s and d. So for that, if you now go from the product to sum, you can now reverse the order to sum to product. All right? So then, now I have in the sum, I have just a single variable. So that's a lot easier to manipulate, you see. So this is the product to sum. This is the sum to product. And then often product to sum is to associate with the induction. And sum to product is often to associate with the equation because you want to make things to be product. So that if you let this to be 0, then one way or the other has to be 0, right? So this is the technique that I'm going to use for proving the, derivative of a sine. Now, sum to product version of that, then the difference here is same thing. If you find the difference of a compound angle, then the alternating term would get double because you subtract, becomes double negative. So instead of a sa co, I have a cosa. That's it. Right? So now we can use this identity for the previous question with the derivative of a sine. Let's take a look. So if I go back, so this is the difference, isn't it? So sine, it was a s and d. So it's a cosa, okay? And the s plus d over 2, s minus d over 2 is what we have inside. So let's try to simplify further. Twice x is 2x. X and negative x cancels out. So that's the limit that we have, right? So now we got this limit. And what we realize instantly is, okay, I must be able to somewhat associate with the sine h over 2 and an h, because that's the almost look-alike with the fundamental limit of trigonometry. But one thing that is missing is that it does not match the rate. It has to be the same. So if I have h over 2 in the denominator, I arbitrarily want to make h over 2, but that's not a problem because I got the 2 in the numerator. If you send in the bottom, it's going to be reciprocate. All of the reciprocate, it's going to be therefore just become the h over 2. Easy peasy. Let me squeeze it. Let me try to put that for you. Yeah, I'm not meant to write the 2 here, so forget about it. It's a typo, okay? So on this one, however, it's matching. The input and the denominator is matching. So the limit will actually converge to 1. Very good. So if I send h to 0, that simply go to 0. So I'm just left with just what is it, guys? The cosine x. And that, my friend, is to fully justify why the derivative of a sine is a cosine using the definition of the first principle. You cannot say the derivative of a sine is cosine unless you're able to prove it. And to do so, it requires to know the fundamental limit of tree. Okay? And there are many variations. What we just saw is a sine theta over theta. Okay? There's another one with the tangent over x, and this is also easy to prove because the tangent is what is it? Sine over cosine, isn't it? So now you can pair this sine over theta to be the fundamental limit of trigonometry, which will converge to 1 as theta goes to 0. Cosine 0 is simply just 1, so it is 1, it is justified. It's sort of a free frisbees, but free gift away. But the arctangent can be harder to prove, but no problem, because we're going to use the inequality that we derived from the exam question. Let's go back to the essential inequality that we mentioned that is very important for calculus, for the study of calculus, especially with trigonometry. So for the proof of that, I need this inequality from the previous exam question. And on this one, what I'm going to do, my friend, I'm going to let theta to be the arctangent x. Oh, wow. Okay. And then, if I plug it in, and then the 1 in the theta and the upper bound is to derive because arctangent is the inverse function of the tangent. So input becomes the output if you composite each other. Right? So then I got the arctangent x and the upper bound to be simply just x, no problem. But then the lower bound is harder to prove because I want to associate the arctangent with the tangent, but I got a sine. So I actually have to convert the sine in terms of tangent so that it's easier composition, you see? And every time you want to convert things out, I really strongly suggest that you stick around with the Pythagorean identity. And the simplest Pythagorean identity I can derive with the sine is to start with the sine squared is equal to 1 minus cosine squared x. That's the simplest Pythagorean identity. And on this one, what I can do is to associate with the secant with the cosine. So cosine is 1 over secant, because they're reciprocal to each other, and it becomes like that. And then why I've done that is because now I understand the secant squared x can be described by the tangent squared thanks to the Pythagorean identity. I got the 1 plus tangent squared x just like that. And now I'm going to do, put it into the common denominator. So if you put into the common denominator for that, I get the 1 plus tangent squared x, 1 plus tangent squared x, minus 1. 1 cancels out. I'm just left over with the tangent squared x just like. Okay, no problem. Then let's try to put the x as arctangent, because that's our aim, wasn't it? But if I put the arctangent here, then thanks to the composition between the tangent and arctangent x, this simply just becomes x. If it's a perfect square, it will come out as x squared, vice versa. But we wanted to describe the sign of arctangent x, so I take a square root on both sides, then only the x will simply change to the x squared, simply change to the x, then this is the lower bound that I can have for my inequality. Now let's put back into the inequality. That's a beautiful, beautiful result. So every time you want to change the ratio, I strongly recommend you to use the Pythagorean identity. Okay, so that was our initial inequality. Then I can change this into x over 1 plus x squared. And what I like to do is simply just divide by the x, right? Because we wanted to talk about the ratio of the arctangent of x over x, right? So, its type is supposed to be 1 over square root of 1 plus x squared. Thanks for the kind understanding. So now I'm going to use this inequality to derive the squeeze theorem. So now let's try to send x to 0. So if I send x limit to 0, this is independent term, so it would simply be the same as 1. But if you look at the lower bound, if you send x to 0, that will be simply just a 1 as well. So in fact, the limit of the arctangent x over x will be also 1. That is great, okay? So that is the proof of it, and I can use it. And this is, I believe, 2021 or 2, November, I believe. I don't quite understand, but I don't quite remember. But it's still an exam question, very recent one. And then the problem actually asks you to use the L'Hopital, and for that you have to use it for quite some time. But in fact, you can easily prove it without using L'Hopital by using just sticking with the fundamental limit of trigonometry. As soon as I see that, oh, okay, I will say, I know something about the arctangent theta over theta. I know something about the tangent theta over theta because they will both converge to 1. But the problem here is, again, which we also have seen it from the fundamental limit of trigonometry, their domain has to match with the denominator. It must be the same rate. So for me, I will arbitrarily put the 2x in the bottom and 3x in the top respectively. But I didn't have it before. So you got to multiply by their reciprocal so that it actually cancels out just to be 1 so that we preserve the form. You know what I'm saying? But if you do that, then send the x to 0, you know this will converge to 1 thanks to what we have proved. This will also converge to 1 thanks to the sine theta over theta. Therefore, I'm just left with 2 over 3. No need to sweat. I don't need to differentiate anything as long as I can use the fundamental limit of truth. So that's very important to realize, you see. Every time I have a room to use it, I will use it. And this is, May 2024 is a very, very challenging problem for some people because often they try to solve this using L'Hopitals only. For me, it's a very hard problem if you are sticking with just L'Hopital, because think about it. Think about the derivative of secant to the power 4. 4 secant cubic times secant tangent. Man, I don't want that. You see? This is very challenging to differentiate because even if you differentiate once, it doesn't fully give you the room to simplify because the secant cubic will still have the product of a secant tangent, and tangent, if you send x to 0, will converge to 0. So you will still have indeterminate form. I believe you have to do twice more, or 3 times. I got no time for that. I don't want that. As soon as I see this humongous identity, I would not start with the differentiation yet. You see? But what can we do? Well, I got a bunch of a secant and cosine. I don't like it. For trigonometry, I like to stick with the one-trig ratio, and secant is actually quite easy to convert because it's a 1 over cosine. Let's do that. So I got the 1 over cosine to the power 4. No problem. Let's put them in the common denominator, which I'm going to have a cosine to the power 4, just like that. And then if you look at my limit like this, it still didn't solve the limit. It still gives you indeterminate form if you send x to 0, but it gives me more hope to simplify because I see this bunch of difference of squares, you see? So every time you see the difference of even power, I strongly suggest you try to do the difference of a square. So I will do the 1 minus cosine to the power of 6 to be the following because cosine to the power of 6 is a cubic to the power of square, you see? So this is the difference of a square I have. Let's go back to the limit that we had. So this is the initial limit form, and I'll change to the difference of a square. In fact, the denominator can be also factorized, right? So if you factorize by the x squared, then I got the x squared minus 1, then voila, I can do the difference of a square once again. No problem. I would not stop. You see, every time you see a room to simplify, you got to do it, right? That's the whole point of math, being able to simplify or optimize. So, and then if I look at the second term here, I now see another factorizable case. In this case, it's the difference of cube, you see? So that's great. So let's try to do the difference of cube. So please remember, this is the factorization of the difference of cube, which is often also seen on the complex number, okay? So then, now I found the bad boy. The one critical limit that caused all this problem is, in fact, the 1 minus cosine x over the x squared, because they are the solely form that gives you the 0 over 0 when you send x to the 0. If you look at the second term here, that would simply be just 1, 1, 1 if you send x to 0, you see? So those are the critical case that I got to convert. That's the indeterminate case that I have to change, you see? So I'm going to stick with just limit of that. Because if I solve this limit, the rest will be just no problem, because it was all non-zero if you send x to 0 other than this one. So let's try to find the limit of this. Well, now finally I can do the L'Hopital. You see, because it's very simple to differentiate. So negative cosine, if you differentiate, you get a positive sign, no problem. Now I don't have to do anything else because I see the fundamental limit of trigonometry once again. So we simply just converts to 1 as x goes to 0. So then 1 over 2 is going to be the limit that I have. You're right. But I understand. Oh yes, I understand your frustration because you don't want to do what? Very good. You don't want to do the L'Hopital, do you? Because we said whole problem here we like to stick with if you can simply just do the algebra. So let's suppose that I'm not differentiating, but try to use the algebra. And for that, often thing I want you to remind you. What I want to remind you here is that if you got the pair of a 1 and cosine, you really want to get rid of the 1. Okay? And how you can get rid of the 1 here, my friend, is to use the double angle of cosine. So 1 minus cosine x is the same as 1 minus cosine 2 times x over 2. And from here, there are 3 forms of a double angle, but the one that with the positive 1 is the following. One with the positive 1 will be 1 minus 2 sine squared x over 2. So onto this, if you expand the bracket, you get the positive 2 sine squared x over 2. So our enemy to pair with the sine, cosine with the 1 is to get rid of with the double angle. That's great. So we got rid of the public enemy of 1. Now you see, I see a very familiar form of the fundamental limit of trigonometry, almost. Okay, so let's try to check if I can use the fundamental limit of trigonometry to evaluate. Okay, well we got a perfect square, didn't we? All right, so maybe I can do the product of itself. And then try to match the input and the denominator. Make sure the rate has to be the same. So I got the x over 2, so x squared over 2. If I separate the x over 2 with x, I almost have a limit, but not quite yet because it's not the same rate. So here, let's do x over 2, okay, arbitrarily. But I didn't have it before, so I got to get rid of it by multiplying its reciprocal. So now this will both converge to 1, thanks to the fundamental limit of trigonometry will be simply just half. Easy peasy, lemon squeezy. That is great. So now I know this critical limit that caused all the indeterminate will actually converge to half. And then the rest will be evaluated because of all non-zero values. So let's see how we can finalize this limit problem. So we had this, this difference of q will converge to like that because this was half. And this is the 1, 1, 1. So that's 3. So if you multiply, it becomes 3 over 2, no problem. So then this was my initial limit. I've changed in terms of something of a cosine, and I can do the difference of a square like that, but we realized this will actually converge to 3 over 2 altogether, right? And then the rest is pretty trivial because the cosine 0 is 1, so the numerator here will become 2, and this is a 1, 1, negative 1. So in the end, you will just have 2 times and negative 3 over 2, cancels out, happens to be just a negative 3. Is the final answer for this limit problem. Again, if you actually try to do this using L'Hopital, you might actually have to do it many, many times, which would have been very challenging to do. The whole point of mathematics is the simplification and optimization. So if you got a room to factorize, please do so before using the method that you already know. You know what I'm saying? But yes, very wonderful problems to associate with the trigonometry and nice animation. Okay, please appreciate. Okay, it's a lot of time. And then the proof with the unit circle was the essence of today's lesson. And then extend it to some other hard exam questions that could be solved much, much more quickly. Okay? So that's pretty much it for me today. I'll see you next time. Thank you!